So I'm just giving you this quick update now because I know you're going to be very busy for the next few days with all of the orientation stuff and so on. So I figured I'd give you just an update of what I've been doing. The last time I spoke with you, I was busy. I finished up the new format for probability density functions, as well as bringing in the average cost. I just started working on that, and I went back to uh, the Roy Billington system, and I got that working. Unfortunately, I don't have the spreadsheet for that at the moment. It's on my other laptop. But needless to say, I got it working for average values. So then I started working on time varying values like you're seeing here. And that's where these new tables that I've incorporated here come in. So what we had previously was just the transformer reliability, the reliability of everything, and then the feed information and custom information, as well as just your average loads that you can work out your basic indices. So the cost stuff included just the averages, and then I worked on the weighting factors. And this is both load weighting factors here, and then if we scroll down, cost weighting factors here. So this isn't a standard format. I've now incorporated probability density functions into all of the weighting factors, because one of the problems I was finding was that in his paper he uses hours per day, month, week of day of the week, and then week of the year, and then in Oliver's paper he's using month of the year instead of week of the year. So I had to sort of find a standard value that I'll work off, and then find a way of incorporating both what they did and what I want to do into the format that I want to use. So I use these formats here, and this is basically a probability density function with two distribution parameters. In this case, the 5 means that it's a beta distribution with its mean and variance. So not the alpha, beta, and scaling factors, but rather just the mean and the variance. And I'll explain to you how I'm going to use that in a moment. So I did that for both load and cost factors so that they scale with distribution with the probability density functions within the day of the week and so on. And then this needed to be taken into, I got my code here today so this is done with this segment here on top. This is my Excel spreadsheet, data incorporation. So it pulls all of these different, all of this data gets pulled into here. And then to explain to you what I've done this week so far, I've worked mostly on trying to develop how I'm going to incorporate the distributions into the code. So this is, for instance, just my selecting which type of distribution. So is it just an average value? Is it exponential distribution, normal distribution? And that gets told to it by that number there that it brings in. So it splits that number and then works out, in this case I'm doing time to failure stuff here. And essentially, just as an illustration of what I'm doing, is given that particular distributions information, it's then extrapolated into different curves, as I've shown here in these two. So this is exponential, normal, and then log normal. And then going down from there, I'll get back to this connection array in a moment, just to illustrate how I use this stuff once I've got it. It then gets extrapolated in terms of this particular table here is the customer outage duration functions. And I had to spend quite a bit of time trying to look up methods of working with probability density functions and averages. So just the average value is simple. You can just take, for instance, this is just two curves similar to what they've got in, I think it's in this paper here. Scroll to the top. So those two curves I showed there are these two curves here. It's both for metal and for retail. So it's that same average cost damage, the individual customer damage function is shown here. So it's easy to interpolate between here using that log, and so on. But the problem I was having was, how do you interpolate between here if you've got a probability density function here and here? So if we go to this paper, they've given the customer distribution function between 1 and 2 hours here. So that's what I've given it here in the same sense. The problem is that how do you, what happens if you have a 5-hour distribution fault? So I'll go back here. So if it falls in here, what is the distribution parameters there? I did a lot of reading on that this week with regards to this paper here recommends using just, if you've got your average value, just take your standard deviation as 10% of your standard. But I didn't feel that that accurately represented what your distribution looks like, because what happens if you have a large dispersion here and then a very small one over here? So how do you connect the two? Eventually I decided, I read into this paper that said the polynomial interpretation. Basically what you can do is, so this is just your average value, you can scale it with a linear value. I didn't find anywhere that did a log-log interpolation. So what I decided to do, and this is another paper that followed on from this one in terms of, this is a statistical paper about particular interpolations of time series. This is an interpolation between probability density functions. So this here says this is how you interpolate variance between 2 points. And this is your standard deviation as well as your mean is up here. So this allows you to interpolate not just your average values between 2 points, but your statistical average. If there's 2 averages, you can find the average at this point, as well as also your variance and standard deviation if you need it. And I'll get back to this in a second. So that's what I started doing with this data here. So for instance, each one of these has a data distribution shown here. So for instance, the reliability data for the yellow down here, you can see this is the probability density function that they use right up against the curve like that. It's very tight to the curve, and that'll be the distribution at that point. And then again, sorry, this is the blue is blue, and then orange is orange. So these are the 4 that, this is how they link together, but I want to be able to link each one of these because there's a difference. There's a 4 to 8 hour. What's the difference if it's a 5? So that's what this next paper does. Well, first, this worked out how I can work out the alpha and beta values given these two. That's just using the work that you gave us in class, using the, I think it was the min-term expression. I can't remember what that name is for that equation, but it's essentially using that to create the alpha and beta values so that you can regenerate them. And that was important for me because then the next step I took was I said, I'm going to take this, and this was just showing how I sucked out particular, I think that's 3.01, so that's the 81131. Oh, it's this value here, my outage duration for 4 hours, and then this is 7, yes, so this is my outage duration for 8 hours. So here, this just shows, or just a proof of concept that I can take that particular type of array combination and remove it so that I can still use it. So for instance, here's my alpha, beta, and S. And that's where that 5 comes from, or in this case 7, because this is giving my beta distribution in terms of alpha, beta, and the location, or the scaling factor. And then this creates the average and the variance for my 2 parameters here, so that it allows me, I can find the 2 values between it. And then this will, it's just finding the new alpha and beta value for a value at 7.88. So all of this basically scales down to, and this is the redistribution for the value at 7.88, just to show that I found a new distribution for it. And this enabled me to do a bit of research here where I took a bit of liberty in terms of, once I found the alpha and beta values for the 2 different time zones, I then did the log-log interpolation of that, assuming that the linear interpolation could be done in the same way that the log-log. So meaning that I took these relationships outlined here, and I just did, instead of just the linear relationship, I did the log relationship in here. So if this was how you found, I don't know if you can see it really clearly, but if that's how you find your x with your linear pattern, you can just do the same one with your log version. So I found that for all 3. I don't know if that's something you can do. It worked out really well, and I'll show you what the results I got here. So this is the plot, the 3D plot, just to illustrate the shape. So that blue duration, this line here, is the 4-hour duration given by that point over there. And this blue line down here is the 8-hour distribution. And then what I did was, in this case, I just, for graphical purposes, I went every 0.2 hours. I created a new distribution. So you can see the line as each one. So it obviously scales as well. So you can see the scaling that occurs, as well as the fact that the lines themselves are redistributed. So that's the probability density function. Let's take an easy one to see. So for instance, this light green one here in the middle is the outage duration for 6.4. Those are the distribution parameters that I calculated using that extrapolation method, and it gave me this distribution here. So I can use that then to find what the cost is, or to generate random numbers at that cost distribution for what I'm using. And I'll explain why I needed to do that, because if I've got a fault there, I don't just need an average value, I need a number of different distributions, a number of different random numbers, so I need a distribution to get that for me. So that was all that I worked on this week, was creating probability density functions between outage durations so I can get cost values. And that's where I got to about midweek. The black line at the bottom is just the average value, showing the relationship as it goes. And then just to scroll back to the top where we were working. So this came to the second part of my problem, was that I didn't know how to deal with. So in this paper, they've given you your interruption cost, your sector interruption cost, and I assume that means that this is a particular user, it costs them $1 for an hour. So I assume you scale that value as they do here by the number of users that is there. So every user you add the number of, so in this case, all of, I think they're using which system? This is bus 2 as far as I remember. So this is bus 2. There's like 200 customers there. You'll scale that with it. The problem was that I didn't want to use just a singular average value because I've just worked out. Let's go down. So I've got a distribution here that shows that's the average value. That all I'll be doing is I'll multiply 200 by that value. But that didn't. I didn't feel too happy with that value because of the fact that the average value in itself won't give you a lot of dispersion. So what I decided to do was to create sort of a connection matrix where, let's go a little bit down here. So when a component fails, you can imagine each one of these is a row to a load point. So for instance, load point 1 here doesn't get a connection. Load point 2 has a connection, 3 and 4 both have connections. These are the weighting parameters that you have from this, but that is based on customers. So for instance, this line here is for retail commercial customers. That would be the weighting function if they had a fault. And then this would be for clothing in industrial. This one would be for metal and industrial, and then the fourth one would be garage and industrial. That would be for every load point you calculate that weighting factor because you need to associate how much every customer base would be associated. And then you multiply that by your customer rate. So this is now at the load point, how many of the particular type of customer is connected. So for instance, this first one we said was retail. There's no customers at load point 1 for that. There's no clothing at load point 2. There's 1 metal, and then there's 10 garage users. So that means that when I multiply this by this, all 3 will pop out a number here, but in this case, because of the 0, it's been 0 rated. And in this case, there's, at load point 2, there's 4 garage users, so that multiplied by the weighting function. So that essentially could be your cost weighting functions. Those that are getting given here get completely adjusted into this. So what it'll do is it's a time of day for all 4 here, multiplied by all 4 of these, multiplied by all 4 of these, then give you that this row values here for, because this is just for retail. Yes, this should be the same for all 4, but in that sense you can create a different version as well. So the big thing here was that those are just average values because you've averaged it out to 0.1. So one of the opportunities I thought I'd take is what I will do is using that probability density function that I calculated below is generate a number here representing how many, or generate a certain number of characters. So you create an array of, let's say, that represents, instead of just multiplying 1 by the average, you generate 1 random number, or in this case 10 random numbers that would fit within the probability density function of the curve. So for instance, this guy here, if it was a 1 hour distribution, will draw 4 unique numbers there for that particular case. So what I mean by that is that instead of having to multiply all of this out, you just generate. So okay, here for customer retail 1, you just have to draw 1. In this case, 0, 0, 1 customer, 10. I need 10 numbers there, and then what you'll do is you'll summarize all of them across that line to generate a total cost to the load point. It's just a computation and a time saver. But that's sort of where I'm at now. So I'm going to work on this for the rest of the week in terms of now creating this at a large scale, because at the moment this is only at a testing scale that it works. But yeah, that was what I did last week, and then just to illustrate the readings. So that was also to do with this in terms of the average loads here are given as per customer. And then just to go to the next section here, I still have to do the load variations that Prof. Gaunt proposed in terms of having different fault times, your time and seasonal dependencies for faults as well. I haven't incorporated, I just have fault times at basis on that. And then the final thing is value at risk was quite easy to do with the average values because you don't have a curve as nicely because your curve is then based on reliability stuff, not on the costs side of things. So it was a bit distorted, but I was able to calculate the value at risk for those average values by working out what was the percentage at the 98 or 95 or 90, depending on what the risk had. And then I read a bit in this paper here was what you should do in terms of the considerations is obviously input data, your risk models, and then you generate your FNA and your indices as well as your value at risk here. And then the last thing was just 3 very interesting papers. This was a paper that generated very similar to Jabulani's paper that was from last year, was to recommend changes based on ECOST, IER, and ENS. This is a reliability monitoring analysis textbook that goes over 4 of the very recent ones. I think this is in 2017. Might be earlier. No, 2014. In any case, they speak to particular papers on reliability. So, for instance, smart grids, electric vehicles, how do they get incorporated into load models, as well as how to probabilistically model home loads and change in that sort of things. And then the final thing, I know how interested you are in metering, and I found a very interesting paper that they developed an automatic reliability calculation system for advanced metering. So essentially they've created smart meters that determine house, customer by customer, reliability indices at home, so using a smart meter. And they're using a particular type of software to do that. I'll send you the paper as well if you'd like. Thank you, man.